It going. There we go. Turn on our stir bar. Let's add some water. See if we get a little vortex going here. That's probably enough. Oh yeah, we got a nice little vortex going there. How you doing there, Frag? How are you, John? How are you? Hello, Isaiah. Nice to hear there, Frag. That's an interesting perspective. I want to try to get this. There we go. Hello, Yash. That looks okay. I'm doing okay there, Frag. Let's do some experiments. I'm going to try something a little different today. Not real different, but I'm going to add. Let's add our universal indicator first. Here we go. I'm going to turn this speed down just a bit. Let's see what happens when I add the universal indicator. All right, and it goes. You notice it's green at first. And then I add it to the purified water. It's not completely purified. Let's watch what happens when that stuff dissipates out into the surrounding water. You can see it stays in the middle of the vortex at first. I'm used to seeing that because, you know, the middle of the vortex, a low pressure region, and material tends to move from high to low pressure, not low to high pressure. So that's why that material is kind of stuck, so to speak, in the middle of the vortex. It's in a low pressure region. It's perfectly happy there. And it'll take some time for that to dissipate. But notice as it does dissipate, the color shifts from green to yellow. And that color shift is because there's carbon dioxide in the water. And that makes the water slightly acidic. So here's the different pH values you're going to see. So the green is going to be neutral. But as that universal indicator leaches out into the surrounding solution with a lot of carbon dioxide, it's going to gain a yellow color from the dissolved CO2. Boy, that's really taking a long time. Let's turn up the speed and try to get it dissipate a little more quickly. That'll suck it down to the bottom, so to speak, and there we go. Push it out. Really like staying in that, that's right, Frag. You can think of it as carbonic acid. Although careful experiments have shown that carbonic acid does not exist in aqueous solution. Hey, Fruit Punch, this is a, let's see, do I believe in the Lord and Savior as a scientist? I apologize, I don't understand the question. Okay, here we go. We're going to go ahead and add. Today, we're going to try adding, we're going to add some milk of magnesia to this. Hey, Giga Bean. So here we go. There we go. All right, now we're going to add milk of magnesia. Here we go. Milk of magnesia is do I believe in Jesus Christ? You know, I apologize. I still don't understand the question. Here we go. I'm going to go ahead and add some White's milk of magnesia to this. Look at that. Isn't that kind of cool? It stays in the center. Now, milk of magnesia has solid magnesium hydroxide suspended in it. It's a white chalky substance, which is why milk of magnesia looks like this. And we can see that as it dissipates into the surrounding water, some of the milk of magnesia dissolves. Now, not all of it does. That's why that's why this is now taking on a cloudy appearance, because there's a lot of solid in here. Okay, so there's a lot of solid white particles. And those, hey, what's going on, Heisenberg? Love the name. And those solid white particles, most of them don't dissolve, but a little bit of them do. And the little bit that do dissolve, they introduce hydroxide ions into the solution, which, as we can see, is increasing the pH. It takes a while for the stuff to dissolve. We're like a pH of maybe 8 or 9 now. But you'll notice this color continues to fade as the milk of magnesia. Now, not all of it dissolves, just a little bit of it dissolves. Never heard of milk of magnesia before. I think people take it as a laxative. They also take it as something for upset stomachs. Gentle relief in as little as 30 minutes. So it looks like people take it for constipation, it looks like. Hey, look at that. We're at well, we're past the blue, so maybe I'm not Heisenberg anymore. We're now at violet. So what we're seeing here is that milk of magnesia, it contains little solid particles, okay? And most of those solid particles don't dissolve, which is why we can't see through this, because those solid particles are blocking the light. However, a little bit of them do dissolve, and that's what's causing our pH shift to a violet color. Now what I'm going to do is I'm going to add a big shot of acid. The acid I'm going to add is hydrochloric acid. So here it goes. This is the same acid that's found in your stomach. It's just this stuff is like 100 to 1,000 times more concentrated. So I'm going to give it a big squirt of this hydrochloric acid. In it goes. We see the color shift to red, of course, because everything has gone acidic. However, the milk of magnesia is still in here. So it's consumed all of the hydroxide, which is why things went acidic. But there's still undissolved magnesium hydroxide left. And that magnesium hydroxide that's in there, remember, it dissolves slowly. And as that dissolves slowly, it's going to consume the acid that I added. Hopefully I didn't add too much. We're going to find out here. I see a slight color shift that has happened to orange. I may have added too much, folks. I mean, I can start to see it's a little bit... I may have added too much, but we'll see. We're just going to let this set just for a bit, and if not, I'll give it another shot of milk of magnesia. We'll start over again. I think I may have added too much. It's going to take too long, so let's just go ahead and... Well, what's going on is some... Oh, there it goes! There it goes. So it took a while. It took a while for the milk of magnesia to neutralize all of the acid that I added. But now it's finally done that. So, it's all shifted back to a green color, so it's neutralized. And then as that milk of magnesia continues to dissolve, we will probably see this neutral green color continue to fade to maybe blue or even violet over time. However, remember that as long as there's milk of magnesia in here, this will look not transparent, so it'll look slightly opaque. I'm going to just add a little bit more. I gave it too much acid to begin with, so we're going to try this again. All right, so I'm going to add another shot of milk of magnesia. This should increase the pH. Here we go. Pop it in there. All right. So I've added some milk of magnesia, which is a white solid. And that white solid, it doesn't dissolve very well in water, and that's why the water's very cloudy. There's a lot of solid particles of milk of magnesia in there, but a little bit of it does dissolve. And the little bit that does dissolve introduces dissolved base, and that's why you're seeing that color shift from neutral to basic. And you're seeing that as the milk of magnesia continues to dissolve, this color will get more blue, and if we leave it long enough, enough of it may dissolve that we'll see a very high pH, at like pH of 10. Okay, so yeah, I can see it. I can see it fading to more a deeper blue. And and what I'll do now is I'm going to add, it's almost violet now, I'm going to add a drop of hydrochloric acid, which should consume all of the dissolved milk of, all the dissolved milk of magnesia. So here we go. Let's add a little drop here. I'm just going to add one. And that's why you see the shift to red. However, there's still undissolved milk of magnesia that is now reacting with the acid that I added, and that's shifting it back to a neutral color. And as the reaction continues, The acid is now neutralized because we're at a pH 7, which is green. It does change a lot, doesn't it? And if we wait long enough, there's still, I think, more of that undissolved milk of magnesia should dissolve, and we're going to see this shift to maybe an aqua and a blue color. I wonder if I should make this warmer. How you doing, Adiyaman? Good to see you around. This is taking a while, so I'm going to just go ahead and add 2 drops here. So let's add 2 drops of acid this time around. 1, 2. So, of course, that's going to consume the dissolved base. But there's some undissolved base present that will slowly dissolve and react with the acid. And when that happens, there it goes. We shifted back to orange, now yellow. And that undissolved base has now neutralized the acid, which is why it looks green. So there's no more acid around. And now as the base continues to dissolve, we should probably see this shift to a deeper green, and then a blue and maybe even a violet color. A chill cat, how did I learn this? I'm a chemistry teacher, and I'm always looking for interesting chemical experiments that I can use to teach my students and just to talk to people about science, which I think is kind of fun. How's it stirring continuously? Heisenberg, like this. See over here? See this little, that's a magnetic stir bar in there, and I'm placing it on a magnetic stir plate. And when I turn the stir plate on, there's a little magnetic fan, so to speak, in this box, which spins, and that stirs that little bar. I don't think this is going to get much more basic. So we're going to go ahead and add 2 drops here. Let's add 3. 1, 2, 3 drops of the acid. That consumes the dissolved base. That gets us to a pH of maybe 3, maybe 4. Now the undissolved base should continue to react. It's going to neutralize that acid. Look, there it goes. It's pulling the pH. We're at pH. Look how quick we got to pH 7. Yeah? So that undissolved base works fairly quickly to get us to pH 7. And then the rest of the reaction seems to take a while. I'm going to go ahead and add a little bit more acid because that's the fun stuff, watching the color change. Let's add 4 drops this time. 1, 2, 3, 4. I've added acid, so it's pH 3. I can still tell there's undissolved magnesium hydroxide in here because this is not transparent yet. So there's still solid particles in here. And those solid particles will slowly react with the acid. There it goes. And bring us back to neutral. Isn't that beautiful? You can still see a stream of red in the middle. Kind of cool. All right, let's add another 3 drops, huh? Here we go. 1, 2, 3. Now, we should recognize that the acid, it is reacting with the undissolved base. And when that base reacts with the acid, it ends up dissolving. So as this reaction continues to go, the mixture in here is going to continue to get more and more transparent as more and more of the undissolved base reacts away. Back to green, baby. Let's add a couple more drops of the acid. Here we go. 1, 2, 3. Amazing how 1 drop gets you from 10 to 7, but you already put 10 more drops in and it's still around 7. This is pretty concentrated stuff. So it's gonna cause some pretty drastic changes in pH. Look at that. It's just gorgeous. It's absolutely beautiful. All right, here we go. We're back to green. The acid's been neutralized. Let's go ahead and add 2 drops of acid this time. So in goes the acid. There's a lot of undissolved base in here that will react with that acid and should neutralize it. It should neutralize it. I am adding hydrochloric acid, Yash, 20% by weight. And look at that. It's been neutralized. Except for that, you can see there's a stream of red in the middle. That stream of red in the middle is because there's a vortex here. And, whoop, not now there's not. When the vortex is there, just like the eye of a hurricane has low pressure, the eye of this vortex has low pressure, and material tends to stay in low pressure regions. Stuff moves from high to low pressure. So if something's already in a low pressure region, it's going to stay there. Hey, thank you there, Sevenelia. I'm sorry if I said your name wrong. Welcome aboard. Let's add a couple drops of the hydrochloric acid here. 1, 2. In goes 2 drops. We're going to see that color shift to red. And then as the undissolved base in here reacts with the acid, we should see a shift all the way back to green at least. Yes, I can use other acids. Unfortunately, I do not have any of those with me. Thank you, Chill Cat. Are you noticing that it's becoming more transparent over time? Remember, it should become more transparent over time. Thank you there, Mobin. It should become more transparent over time because the solid base particles dissolve when they react with the acid. So that's why we're seeing it get more transparent. And when all of the base reacts away, it will become transparent. And when I add acid, there'll be no more base present. So it'll be both red and it'll stay red because there's no base left to react. Here we go. Let's add 2 more drops of acid. I don't know if there's going to be much left here. Oh, no, I can see it shifting to orange, orange, yellow, yellow. So there's still a little bit. Now it's green. There's still a little bit of that undissolved base present, but it's really starting to get transparent. This might be the end. I'm going to add 3 drops here. This might react away all of the solid. Let's see. That's looking really close to transparent. We might have to add some more milk of magnesia here. I agree, Chill Cat. I think the tornado changing color is quite beautiful. Oh, no, I can see it changing to orange. There must be a little bit of the undissolved solid yet left. Yep. The only way that's going to shift back to green is if there's some base present. Why 3 drops, Adiaman? Because no one's telling me to add a different number. You guys want to see a different number, you just let me know, all right? I'm going to go ahead now, and this is almost transparent now, which means there's very little milk of magnesia left in here. So I'm going to go ahead and the dose matters. Come on, Mobin. Everything is poisonous and nothing is poisonous. The dose makes the poison. What was that? Paracelsus. Ewald wants 4 drops. You got it, bud? First, I'm going to add some more milk of magnesia. In we go. So this is it's a little bit of water. And in that water is suspended a lot of solid milk of magnesia. And yes, Yash, you can think of this as a neutralization titration. You can think of it that way. So now, yeah, we're pH, we're like a green or aqua color. So our pH is, I don't know, somewhere up around 8 maybe. Yeah? Okay. So let's add, 4 drops. That was the suggestions. The suggestion was 4 drops by Ewald, so that's what we're doing. Heisenberg's saying 9, but looks like we're doing 4. Here we go. 1, 2, 3, 4 drops. Of course, the acid rapidly consumes any dissolved base. And now, the base that is not dissolved, there's quite a bit of it. I can tell that because it's not transparent. The base that's not dissolved will react with the acid that's been added. And there we go. It's pulling back to pH 5, 6. When it gets green, that's really close. There it is, pH 7. And if we wait long enough, more of the milk of magnesia should dissolve and get us to pH 9 and 10. I want to try this. I was using for this one, I was using distilled water. I want to try alkaline water for this one, all right? We're going to try essential water. They say it's pH 9. So we're going to try that for this flask over here, okay? Let's get this one going. A little alkaline water. We'll add the universal indicator. We'll try the same experiment with the milk of magnesia. I don't know what's going to happen. I just want to fiddle around here. Here we go. In goes our essential water. We'll add a little bit of universal indicator. We'll try the same experiment. Well, that fits nicely. Okay. Universal indicator time, folks. Here we go. Squirt number 1. You can see the universal indicator is a nice green color. In it goes, and it turns violet because, as advertised, the pH of the alkaline water is like pH 9.5 or higher. So they are telling the truth there. There we go. We'll give it 2 nice squirts. Get a nice violet color going. Nice and beautiful. You can see it's transparent over here because I haven't added any milk of magnesia. This one over here is not transparent because that one does have some of the undissolved solid in it. Let's go ahead and add like 2 drops of the acid over here. And we know what to expect over there. Turns to a red, and slowly over time, look at that, it's already orange. So long, Adiyaman. There it is, slowly over time. That's fading back to orange, yellow. So past thing is adding, why purple? Why is this purple? That's purple because to this flask, instead of adding purified water, I added essential water, which, the pH of this stuff is pretty high. So here you go. Here's like over here, this is neutralized now. These are the different pH values you're going to see in each flask, okay? This is not bromothymol blue indicator. This is universal indicator, which is a mixture of 4 different indicators, of which one of the indicators in universal is indeed bromothymol blue. I'm just going to turn this like this so we can see both flash. It's a little easier. Try that one more time. Okay, now to the flask over on the right, I'm going to add some milk of magnesia. It's solid magnesium hydroxide, suspended in some water. So I can just take some of this. It's also got mint flavor, which I can smell, but you all, of course, can't. Here we go. You can't note that, but it does got a mint odor to it. I'm going to pour this in, and it stays violet because milk of magnesia is indeed basic, okay? So I'm not surprised to see that the pH remains 9. Yeah, it is mint flavor. Here you go, no. Fresh mint. So yeah, people take it, apparently they take it for a laxative or an upset stomach. All right, here we go. I'm now going to add some hydrochloric acid to this over here. Let's add like, I don't know, 1 drop, see what happens. Not a whole lot. Let's try 2 drops. There we go. Oh, that's gorgeous. Let's try 3 drops. Isn't that beautiful? Let's try our 4th drop. Oh, man, that's so pretty. I'm going to try another drop. So, as I continue to add acid, the pH continues to drop. But when I get it red, right there, I'm going to stop adding acid. And what's going to happen now, the solid magnesium hydroxide in here that hasn't dissolved, it will continue to react with the added acid. So you look, the pH is rising as the milk of magnesia that's in here reacts with the acid I added and neutralizes it. The same thing's happening over here. Thank you there, no. I'm going to add like 3 or 4 drops over here on the left. So yeah, over here on this flask, the milk of magnesia has neutralized the acid. And as that milk of magnesia continues to dissolve, this pH will continue to rise. I'm going to add just a little bit more milk of magnesia. How you doing there, Rambling? Yeah, the gradients are gorgeous. I agree. They're really pretty. Give this another shot over here. Get in there. Let's change that pH, baby. We want a high pH. We want to see some major color changes is what we want to see. All right. Let's add a drop of acid over here on the right. Excuse me, on the left. Another one over here on the right. Yeah, it's going quick. Just a Kid changed their channel name, so you've been in one of my lives before. Cool, Just a Kid. Nice, no, glad to hear it. Yeah, face reveal at the end, past things. I usually just flip the camera around and talk to folks. Wow, Rambling doing it. What you doing the history of there, Rambling? I want to try this. Let's just turn this one off. I'm gonna turn this one off. We'll add some drops over here so we can see some color changes while I'm fiddling around. We're gonna leave this one off, and we're gonna see what happens if I just start adding acid to this. All right, let's see what happens over there. Weirdos, huh? That's cool. It's like the red and green over here at the same time, which is kind of cool. I'm wondering what's going to happen. Look right there in the middle, man. Look at there in the middle. You can see this flash of yellow. And it's like the acid is like, it's penetrating down the flask. It's kind of cool. But there still should be some milk of magnesia in here that should react with this. And so we should see a color shift back. I don't know. What? Did I add enough acid to completely neutralize the milk of magnesia? I don't know. I'm going to try. I like this. This is kind of cool. Do the same thing over here. 1, 2, 3, 4, 5. Let's just see what happens. Some beautiful swirls. Oh, look at that. Look at that. It's pretty. It's like a stoplight, huh? Absolutely like a stoplight. Interesting. Alan, I'm not sure I understand the question. I mean, I can throw a lot in there. If I put too much in, what'll happen is all of the milk of magnesia will react away. It does look artistic, Heisenberg. And look, the acid over here has been consumed. Yash, great to hear it. Yash, taking some physical and analytical chemistry. That's near and dear to my heart. You can tell the acid's being neutralized over here as well, just more slowly. I'm going to try adding some acid over here again. 1, 2, 3, 4, 5. Give it a quick stir and then turn it off. We'll see what happens. Very pretty. Cool stuff. Cool stuff. I'm going to give this one another squirt of acid because it looks like everything is reacting away. There's a big squirt. That's gorgeous. You can see the acid settling down to the bottom. So why would the one on the left go slower than the one on the right? Because I've got more milk of magnesia over here. There's a lot more milk of magnesia added. And chemical reactions depend on the concentration of the reactants that you have present. So that's my guess. Give it a little squirt over here. Quick spin. Oh, man. I'm going to spin this. I think maybe all the milk of magnesia may have reacted over here on the left. Let's see. Yeah, I think so. So now what I'm going to do, while this one over here on the right is doing its thing, I'll add milk of magnesia to this while it's turned off. See what kind of interesting patterns we can get. Not real sure. No. Yeah, I do this for fun, but I am a teacher. Not when it's zero order, Heisenberg. You got it. Absolutely. Zero order. That's independent of the concentration of reactants. I've taught everywhere from the middle school level up through the university level. There's the milk of magnesia going in, little drops of it. That's kind of cool. They're falling to the bottom. There's a bunch of solid milk of magnesia that I've just added to this flask over here on the left. You can see it settling down to the bottom. Going to give it a quick stir. And we're going to see what happens over there. Look at this. Down there on the bottom, it's kind of like a red color. Interesting. I think I'm going to add a little bit more acid over here. Here we go. How you doing there, Henry? Good to have you on board. Hey, Henry, don't spam the comments. You get one warning and then you're gone. All right, a chill cat. Good to see you. See you, Henry. That's beautiful. We got some beautiful colors going on over here. It's kind of nice on this side. We got all the different colors. How you doing there, Sam? It is pretty over there on the right, man. There's some cool stuff going on. Very cool stuff going on. I agree. No. It is very pretty. And down here at the bottom, what's nice about it, where there's a lot of acid, you can see is transparent because there's where there's the highly acidic, you're going to need no milk of magnesia. So there should be no solid here. But watch as we move up to higher pH, it gets less and less transparent. That's so awesome. That is so awesome. You can totally see what's going on there, right? When there's a lot of solid milk of magnesia suspended in the fluid, you can't see my fingers and the pH is high, as you would expect, where there's a lot of the base around. And then as you move to the higher acidity, it gets more transparent because there's not going to be any of the solid around. How you doing there, Rat Razor? Yeah, that's cool. We got a nice little rainbow going over there on the right. It's pretty. Oh, yeah, Mobin, I think most people want to drink this. Absolutely. I wouldn't recommend it. Isn't that cool? No. Oh, that's cool, Heisenberg. Yeah, it's like two different pH gradients. This one runs from pH 3 to pH, I'm going to say 7, 7.5. And this one's going to run from pH 3 all the way to like pH 8 or 9, which is really pretty. A very large green region over here. Quite there. There's your neutral pH region. There's a very thin neutral pH region over here. All right, you want to mix them up? Which one do you want to mix? The one on the right or the one on the left? Well, good guess. I don't know. What do you think will happen if we stir it up? It's hard to know. It depends on the balance of acid and base that's present. Mellow Jello says both. Alan says the left. Be Wise says the right. No says the left. That's 3 votes for the left to 1 to the right. We're going on the left. Here we go. Now, it looks like it's gone red, but I think this is going to continue to go up in pH because you can tell it's not quite transparent. So there it is. We're now at pH 4 or 5. Now it's pH 6. As the milk of magnesia continues to react with the acid, that's going to go green, man. That's going to go green. All right, we'll do the one on the right now. Although I kind of like to see it over there, but we'll go ahead and give it a shot. Here. Let's see what happens here. Give this one a swirl. Oh, that one's going green immediately. Very cool. Very cool. You guessed right, Heisenberg. All right, add a drop of acid. Add a drop of acid. There's plenty of milk of magnesia around still to neutralize the acid. What if we I'm just going to put a boatload of this stuff in here. Just put a boatload in. Ha ha! Do a bunch, man. Do a bunch. We're going to let this one, look at this, has got a ton of milk of magnesia in it. That's why, you can't even see through this, not even close. Yep, so the speed of the stir bar and the size of the stir bar both matter. I'm going to wait till this one gets like a nice blue color. It's like an aqua. It's like a muddy aqua green. All right, here we go. Let's add just a single drop over here and see what happens. In it goes. can't even get down to the bottom, man. 1, 2, 3 drops. You know what? I wonder what happened if I had base. Yeah, like a weird smoothie indeed. Like a weird smoothie indeed. Add a bunch of acid. Chase it with a little base down the middle. It is like a weird smoothie. I love it. Put an LED light in there. We can do that. I'm going to put an LED in there like this. Like a color changing LED. Too much light going on, man. I'm not sure that would really show much. How you doing, AE Master? All right, let's add some acid over here to this side. I wonder. Hey, Crunch Master, how are you? Oh, that looks interesting. Just playing around with the light a little bit here. I think that looks cool. Oh, yeah, that looks awesome. I'm loving it. There it goes, changing back. Changing back. Look at that. That's gorgeous. Oh, my gosh, that's so pretty. Try a white light behind the beaker and less light overhead. So that's what I do have. I've got white lights behind the beakers there, DJ. That's what I've got going on. And I turned off the overhead light. So the overhead lights are off. So I appreciate the confirmation that what we're doing here is going to look pretty cool. We can take this LED out. It's not doing anything. Forbidden lime smoothie and grape soda. You know what? Let's make it strawberry soda, shall we? Oh, it didn't want to go. So AE Master drops their favorite element in the chat, indium. Have you ever chewed on indium, AE Master? Everybody dropped their favorite element in the chat. Mine happens to be hydrogen. Wonder what others. AE Master, you did not come in early. We're about 40 minutes into the live at this point. So I haven't either. I've always kind of wanted to ever since I saw a couple videos on that. I love how the background light kind of changes as this color changes too. I want to chew on some too, Alan. Tastes like grape. Metallic grape. Come on, man. Well, maybe, right? Ah, nice to hear, Heisenberg. I'm glad we calmed you down. Have a great sleep. Oh yeah. Yeah, I saw Vsauce chew on it too. You guys see my recent video where, Vsauce is selling these curiosity boxes. I don't know if you've seen them. The Curiosity Box folks asked me to make a video on their Curiosity Box. They're selling these bricks that are metallic, but they're shaped like Lego bricks. And so I did an experiment on those metallic blocks, and that video is starting to go viral, man. I mean, the last I saw it had like 700,000 views. It's a short video, but what's kind of fun, well, you have to check it out and let me know what you think. Chlorine. No-no's liking some chlorine. Do we have a swimmer? Are you a swimmer? Is that why you like chlorine, or you just like it? Thank you there, AE Master. Appreciate it. A Kiwi Co pack back then. Thanks, No. Let me know what you think. You should be able to find it pretty easy if you just go to my shorts. Sort by popular. It's going to be down there around 500,000 or so. Alan's liking some nitrogen. I agree, DJ. We can really get some cool shots out of this. I totally agree. It's just pretty, man. Just pretty. All right, let's add some bait or some acid here. We got too much violet going on. Look at that. It's just so stinking beautiful. Look at that. Let's add a little bit more acid. Get on in there. Come on now. Add a little bit of base up here at the top. Try to get the whole rainbow going. Ramblings. I apologize. No, citrus acid is not an element. We actually call it citric acid. Citric acid is made of the elements hydrogen, carbon, and oxygen. But you know what? It can be your favorite chemical, Rambling. So there you go. Your favorite chemical, it happens to be a compound, is going to be citric acid. Why do you like citric acid? Do you like sour stuff? Ooh, we got some pretty colors going on. Beautiful colors. We got any, so it's element, plants need it. Try citric acid on the red one. I don't have any citric acid with me, unfortunately. We got any scientists in the chat today? Oh, yeah, Rambling. Like Sour Patch Kids? Absolutely. Loving me some Sour Patch Kids. Tell me about it, Alan. Tell me about it. I'm late to the show, so I didn't catch what you started with here. What is it that is reacting to the acid and base? Great question, Double Wide. Yeah, sorry, the comments are coming through kind of slowly, it looks like, folks. So what's going on here? What is happening here is that in each flask, I have added something known as, well, it's water, and then I've added universal indicator. And to the universal indicator is going to display these colors. Let me get them out here. I'm going to turn this light on just so you can see it just for a bit. It's going to display these colors depending upon pH, which is how acidic or basic something is. So over here on the right, that's kind of like a yellow color. That's going to be a pH of 6. Maybe it's pH 5, somewhere in this region, which is going to be slightly acidic. 7 is neutral. The further below 7 you go, the more acidic you are. Over here on the left, you can see that this is violet. That's going to be a pH 10, which is quite basic. And then I just add either acid or base to each flask, and we watch what happens to the pH. We watch what happens to the colors. Yeah, Double Wide, I like it. It's like a liquid litmus strip, except litmus only displays 2 colors, red or blue, whereas this stuff displays the whole rainbow of colors. So this stuff is really kind of cool. But I like that. It's a liquid litmus strip. What a great way to describe it. I guess I should just say it's a liquid pH strip. Hello there, Scarecrow. Dark matter. We are getting some gorgeous color changes today. I don't know what's different about the setup, but I am seeing some interesting stuff. That's correct, Alan. You can make this type of liquid pH strip from red cabbage. We call that red cabbage indicator. That's right, Heisenberg. Heisenberg, I thought you were going to bed. So, yeah, you can make this stuff with red cabbage. Thank you there, No. It's got some prettiness going on today. Ah, gotcha. Chem's keeping you up. Am I using hydrogen hydroxide? Yes. If you buy hydrogen hydroxide, you mean water? Yeah. So both of these are, primarily water. Okay, sodium hydroxide. Yes, AE Master. The base that I'm adding is sodium hydroxide. Thank you there, Scarecrow. I appreciate that. Oh, man. Hello, sir. Can I drink that when it's neutral and is pH? Asks past thing. So, past. You wouldn't want to drink this when it's neutral. While, you know, the acid and base would have completely neutralized each other and you would have salt water at neutral pH. The issue is the indicator that's been added. The indicator that has been added contains 4 different dyes, and one of those dyes is a laxative. What a great question, Alan. What a great question. I'm curious. I don't know. I've never done that. I've never put sodium in very cold water. Yep. Beautiful colors going on today. Beautiful colors going on today. Welcome back, Crunchmaster. Welcome back. Yeah, I imagine it'd be slower. It is, Michael. Hey, Universe, welcome. Welcome aboard. Thank you there, Fish. Great to have you on board with us today. Doing some experiments with universal indicator, acids and bases, just watching some color changes, talking about life, talking about chemistry, talking about science. How you doing there, Akiko? Good to see you. I apologize if I'm not saying the name correctly. Feel free to correct me. I like how the lighting changes when this pH gets high and the solid shows up and starts to block the light. It changes everything that looks here. What's the difference between a litmus paper and a pH tester indicator? All right, Remy, you got it. So litmus is a dye that changes color depending upon whether it's in an acid or a base. So it'll be red in a base and it'll be blue in an acid. This is also an indicator, and we can call this a pH indicator, the mixture of dyes that I'm using. And they do the same thing. It's also an acid-base indicator. The difference here is that it'll show a wide variety of colors in acid or base. So instead of just showing 2 colors, red or blue, like litmus, this shows the whole rainbow of colors. How you doing there, NRM? Universe's favorite element is tungsten. That's heavy. I'm loving it. Beautiful color changes today, babe. Beautiful color changes going on. Starting to run out of my acid and base. Now we're about halfway. Oh. Storm chasers. Storm chaser watching. Does this look like a storm to you, Storm chaser? Your favorite element would be something very radioactive, says Remy. Yeah, DJ's loving some oxygen. The solid on the left. Aluminum. Remy likes radioactive stuff. Storm chaser likes, Alan likes storm chasing. Hello, rambling. You got tears when you took chemistry. Welcome back, rambling. Look, man, I got to tell you, I think a lot of students experience frustration when they take chemistry. I know a lot of my students do. They tell me. Chemistry is, it's tough to learn and it's tough to teach, I get a lot of students that do not enjoy my teaching, that's for sure. True, Be Wise. So Universe is asking, why is this one cloudy? The reason why this one is cloudy, Universe, is because to this flask, in addition to the water and the universal indicator, I've also added milk of magnesia. And milk of magnesia is basically a bunch of solid particles of magnesium hydroxide. So there's some solid that's suspended in this one here, and that's what's sort of given the grainy appearance to this one over here. How do you do that? Asked Fernie. So, Fernie, all we do is we just take water, and to the water we add some universal indicator. And then to the universal indicator, we either add 20% by weight sodium hydroxide or 20% by weight sodium hydroxide. And it's about a liter of water. Let's find out, DJ. So DJ is asking, what happens if I put in equal amounts of acid and base at the same time? So what we're going to do first is we're going to get this to be neutral, okay? Let's get this neutral. That might take me a little bit. I think that's going to be green. Come on, baby. You know what? That's close enough, all right? So DJ double wide, what I'll be doing over here in this flask is I'm going to add equal drops of these. Now, the issue is you got to understand, I'm not certain that these are both exactly the same concentration, okay? So here we go. We're going to find out, though. So in goes a drop of base, in goes a drop of acid. So you can see it went slightly more basic, and that tells me, since I did a drop of each, that the base is slightly more concentrated. So I'm going to add another drop of acid here. And it looks like that got us back to neutral. So roughly speaking, this is going to be twice as concentrated. The base is going to be twice as concentrated as the acid, roughly speaking. So for every drop of base that I add, I'm going to add 2 drops of acid. And that should go back to green. And sure enough, it does. Although I think that's closer to like a pH of 8 right now. So I'm going to add a 3rd drop. So maybe it's looking like for every 2 drops of this, I'm going to need 5 drops of the acid. Hello there. Yay, chemistry. I apologize, Cretino. I'm not sure I said your name right, but I gave it a shot. If hypothetically my tongue is acid-proof, how sour would sulfuric acid be? I imagine it'd be pretty sour. But, you know, Alan, that would depend on the concentration of sulfuric acid. What if I put a gumball on it? How you doing there, the administrator? Good to see you. I imagine, too, the same universe. I guess it would taste pretty sour. What does dry ice taste like? Rami, I think I kind of know this. So, I go to the store sometime to buy dry ice, and it's kept in this big container. And thanks, Cretino. And so I'll open up the big container, and of course, there's going to be a bunch of carbon dioxide. There's just a bunch of carbon dioxide gas. And sometimes if I inhale that in, it's like, like sometimes if you get like too much soda, like I remember when I was a kid, sometimes you'd drink soda and you'd laugh. And the soda would, you'd laugh and the soda would come out your nose. And I remember that experience where what it felt like when the soda would come out your nose and all that carbon dioxide would get released. It's kind of like I don't know how to describe it, man. But that's, to me, what it kind of, quote unquote, tastes like when I inhale in a lot of carbon dioxide. So, administrator, I'm doing well, trying to qualify for a physics competition. Tell me about that, administrator. Isn't acid just like water with a high pH? Or how do they make acid? So, DJ, hello there, Mike. The chemical definition, there's many ways you can define acid, like 3 different ways. Rambling, I buy it at a store here called Meyer. So the chemical definition of an acid, or one of them, and the one that's appropriate, I think, for what we're doing right now, is a substance that releases protons, H+ ions. That's kind of right, Cretino. What you're looking at is some water to which universal indicator has been added. Universal indicator displays these colors at different pH values. And so like over here, it's red. So that's a pH of 3 over here. And over here, we're green. So we're neutral over there on the left. The International Astronomy and Astrology Competition. Interesting. Now, I'm curious as to why it's astronomy and astrology. Astrology, in my understanding, and I think most physicists' understanding, astrology is not considered to be physics. It's considered to be pseudoscience. So can you give me a little information about why they include astrology in the competition? Rambling, that might work. You know, you can just Google where can I buy dry ice near me, and some things might pop up. Hello there, Zabler. If you use a dropper and put it on paper, would you see the paper turn? Yes, that would happen, dark matter. So what we would do is we would want to infuse the paper with... you got it, administrator. I was just like, what the heck? You got it. Can I make dry ice at home? You can. If you have like if you have a fire extinguisher that just releases carbon dioxide and you release it really fast into a cloth, you can sometimes produce tiny flakes of dry ice. Yeah, I think it can be done. I just go buy it because I want to do the experiments. So a sock, that would work, universe. What a great idea, huh? That's cool, administrator. I hope it goes well. Man, are we getting some beautiful colors today. All right, folks, I'm getting close to being an hour doing this. And I can tell because my muscles are starting to get sore. I played a bunch of sport this morning, and I'm an old man. And, you know, when you get old and you play a sport, you tend to get stiff if you sit too long. And I've been sitting here for a little too long. So I'm gonna flip this, flipping the camera around. You're gonna see my ugly mug. So just know if you don't want to see a 57-year-old man in his basement, then now's the time to get the heck out of the live. You have been warned. It's gonna be coming at some point, okay? The Ranger. I thought that was a commercial airliner or a commercial airplane. That's my understanding. Yes, that's right, Rami. I'm a 57-year-old dude. Well, thanks. I don't sound 57. What's it just makes me wonder, what is it? What does a 57-year-old sound like? Hey, thank you there. Thank you there, DJ. Can I do this? Can you do the science behind the sonic boom? What a great idea. I'd have to think about how to do that. Are there any water-soluble tungsten compounds? I'm guessing tungsten chloride, but I don't know. Wow. Alan, I would try, instead of sodium hydroxide, I would try maybe potassium permanganate. Tungsten oxide, I think that's going to be insoluble. Hey, thanks there, Trone B. Hope to hear, how things go with the red cabbage. All right, let's turn this thing around. All right. Flipping time. How we doing, folks? Let's turn this light on over here. Get the lighting going. Hello, administrator. The administrator asks, why do some formulas include a Roman numeral like 2 in it? Hello, administrator. So the reason why we do that, so like you say copper 2, it'll always follow a metal, and the 2 stands for the positive charge on the metal. And so if you see something that says copper 2, then that means the copper ion that's in the compound has a +2 charge. That's it. So if you see like a Roman numeral 4 behind something, lead will do this sometime. So lead 4 is just the lead ion, the lead metal ion with a +4 charge. Thank you there, Theo. Great question, Theo. Let's get to that. Theo asks, why do some color changes start at the surface while others start at the bottom of the glass? Let's get to that question. Here we go, Theo. All right. So here the vortex is not running. All right, Theo. And this is red, so I'm going to add some base to it. And if we add base, we're going to see color shifts up this way. All right. So now there's no spinning going on. Okay. So here we go. So if there's no number behind it, does it have a negative charge? If there's no number behind the metal is going to have no charge. Here we go. I'm going to go ahead and add some of the base in. And you can see right away, you can see as it falls, it's changing to a violet color. Now it drops because the base is more dense than the surrounding fluid. All right, you can totally see it just sinking in there, and that's because the solution of base is more dense than the solution of acid that I'm adding it to. Okay, now you ask, why does it sometimes go to the bottom first? Let me get it back to red here so I can answer that. Let's get it back to red. Now, in this case, what we have to recognize is, I'm going to turn this down just a bit. There's a vortex going. And when there's a vortex going, you got to remember, just like the eye of the hurricane is low pressure, the eye of this vortex is low pressure. And material tends to move from high pressure to low pressure, but not low pressure to high pressure. Okay? So if I add material to this, it's going to stay in the center. But it will move down to the bottom. And when that moves down to the bottom and it hits that stir bar, it gets pushed out along the side. And there you have the color change occurring at the bottom first. So it stays in the center, gets pushed down to the stir bar. And then there, when it hits the stir bar, it gets pushed down, out. And that's why the color change appears to happen at the bottom first. So that's that question there. How much acid does it take to vaporize a 70-kilogram chicken? A lot is right. A lot is definitely right. So yeah, I stopped reading the comments there a little bit because Theo's question took a bit. So here, let's look at this one. Can I please explain why iron sulfate and oxalic acid are mixed? Iron oxalate forms despite sulfuric acid being stronger. So I'm guessing that's driven by precipitation. So just help me out here, universe. Is a solid formed in that reaction? Is the iron oxalate that's formed, is that a solid, a precipitate? And if so, that's what's driving the reaction. That the formation of the solid is going to drive the reaction. You got it there, Cretino. Do I think it's physically possible to turn something like aluminum into real gold? So be wise. Yes, but it's really hard. So, when chemistry first took off, people started to recognize that the atoms that you started with in chemical reactions didn't change in chemical reactions. So the atoms that you start with in a chemical reaction are the same as the atoms that you end with in a chemical reaction. They just get rearranged. So like you can have water, which has hydrogen and oxygen, that can react if you apply electric current to it. You can make hydrogen gas, which has hydrogen atoms, and oxygen gas, which also has hydrogen atoms. So the atoms you start with and the atoms you end with, they stay the same. Well, once folks started to figure out about the nucleus of atoms and that the identity of an atom is captured in its nucleus, specifically the number of protons in the nucleus, like aluminum has 13 protons in its nucleus, people started toying with nuclear reactions, which are different than chemical reactions. And they were able to do these processes at a higher energy, which allowed you to manipulate the nucleus. And if you can do these high energy nuclear reactions, it is the case that you can transform one element, one type of atom, into another. By causing it to, that nucleus can either gain protons or lose protons. Now, nobody's ever changed aluminum into gold, But when people figured this out, I think Linus Pauling was one of the people who decided they were going to do this. They were able to change bismuth into gold through nuclear reactions. I think that's right. I think it was bismuth that they used, but you might want to check me on that. No, that's right, Universe. When aluminum was first discovered, it was very expensive until they figured out how to make it on the cheap. Yeah, when was aluminum discovered? I don't know. I don't have that's not up there in my brain. Thank you there, Be Wise. Yeah, and Be Wise. What's funny is I think it was Rutherford and Soddy. These were the two scientists who first. How you doing there, Ruben? Um, Doing great, Shark Bite. So, Be Wise. When people were first figuring out that you could manipulate the nucleus and change one element into another, this was revolutionary because people just were familiar with chemical reactions. So they thought the atoms you start with have to be the same as the atoms you end with. And when Soddy, who was working with Rutherford, said, hey, this is kind of what I think what's going on, Rutherford looked at him and he agreed. And he was like, this is the quote. I'm not going to have it exact, but it's close to this. He said, my God, Soddy, they're going to have our heads as alchemists. Which is what was happening. It was actual alchemy. You're changing one element into another, which, in the scientific community at the time was taboo. But, once people kind of say, okay, yeah, you can manipulate the nucleus and you can make different atoms, it's just like, it's what we do in science. When you learn new crap, you change your mind. Thank you there, Life is Good. Great to have you on board, Noel. Isn't iron the closest element to gold? It is not. So what is it? 70. Mercury is one atomic number higher than gold. And, oh gosh, how's it go? Iridium, platinum, gold. So platinum is one atomic number less than gold. I'm telling you, man. Well, be wise. You should know that Rutherford is very well known in the physics and chemistry community. Thank you there, Theo. I appreciate it. That's correct. No, that's exactly right. So when you do nuclear reactions, one element gets changed into another. Oh, you're looking this way on the chart. Yeah, Heisenberg, if you're looking this way on the chart, sure. Copper is right above silver, which is right above gold. I don't know if I want to know why they're rambling. I have not. All right, folks. My neck's starting to hurt. Yeah, great, Be Wise. Be interested to hear how what you think. I'm gonna call it a day. Thank you for checking out some of the beauty of science with me today, enjoying some of that. If the Earth has a tilt of 23.5 degrees, does that mean the North and the South poles get uneven heating? Yeah, at different times of year, right? At different times of year. So, that's why the North Pole is going to be winter at some point and summer in the South Pole and vice versa. Okay, Alan, let's answer this one. So Alan asked, if the heaviest thing a star can make is iron, how do we have stuff like uranium on Earth? I wish you luck there, rambling, but I don't believe in luck. So actually what I wish you is a clear mind and lots of motivation. You got it, universe. That's the idea, right? So stars in their nuclear furnaces, they in their cores, these nuclear reactions happen. And basically what happens, you start with hydrogen, and the hydrogen atoms fuse together to make helium. The helium atoms are going to fuse together to make some beryllium and some carbon, and everything's going to fuse. You're going to make some magnesium. You keep making larger and larger and larger elements, but only to a point. And that's because there's it's energetically favorable to continue to do this process up to iron. Iron, nickel, somewhere in there, cobalt. But once you get there, it kind of stops. And so what happens once you hit this is kind of, you don't make any larger elements. Well, how the heck do you get elements larger than iron then? What a great question. That's an absolutely perfect question to ask. Well, one way, there's multiple ways, but one way you can get larger than iron elements is when the star runs out of energy, it runs out of fuel, and it can no longer produce these nuclear reactions. So what goes on in a star? A star is a balance between some really wild forces. So what you have is gravity pulling the star together, and then you have these nuclear reactions happening, heating all the gases that are pushing it out. And when you have a balance of the gravity and the nuclear heating expansion, when those balance, you've got a stable star. Well, just think about this. If you run out of fuel, you don't have anything pushing the star out anymore. And so when the star runs out of fuel, it literally just goes, well, boom, it crunches. And it crunches so hard that it implodes, and then there's a shock wave that blows everything back out again. And that's what a supernova is. And the energies involved in supernova explosions are so incredibly high that you can then have the energy that's necessary to take iron and start fusing them together to make larger and larger elements. And so that's just one way that we get some of the larger elements. Absolutely, universe. Absolutely. All right, folks, I'm going to call it a day. That was fun. You guys had some great questions today. I wish I could still hang out, but I gotta take it easy here. Like a hammer bouncing off an anvil. I like that. Tell your mother hello there, Ruben. Ariane Singh, great to have you here. I don't think so, double wide, but if you learn different, you let me know. Ariane Singh, great to have you on board, and we're going to see you all next time. I usually do these on the weekend, Saturday or Sunday, usually Sunday afternoon around this time.